part A, we have 1/2 page. I want to delay it after we complete part B when we do the summary, because that half page also summary. So those two summaries are correlated. So I put them together. Okay, yeah. So we have half page left in part A. Yeah. So we will do later. Yeah. Yeah. The topic, part B. Just a minute. Yeah, I need to get my remote control. Yeah. Okay. All right, remote control. Yeah. Let me try. It works. Oh, yeah, it works. Yeah. All right. The topic here, growth functions. Yeah. So it's a abstract concept. Yeah. So, but we need to use this concept to help us understand asymptotic notations. Yeah. All right. B.1, introduce growth functions. What's the definition? What's the meaning? All right. Now, we want to compare our running time function and number of basic operation functions, because these two functions are related to efficiency problem of algorithms. Yeah. Now we want to study efficiency. What's the best way to describe the efficiency of algorithms? Yeah. Notation. Yeah. So we use this capital T of n represent function of running time. Yeah. So when you run your programs on your machines, yeah, you clock it. Yeah. So you have a running time function. Okay? That's a capital T function. But there is another function. Yeah. So we count number of basic operations. So what is basic operations? Here, yeah. Because in an algorithm, we may need to use multiple operations, right? For example, in our Module 1 part B, evaluate polynomials, we have multiplications, we also have additions. So which one we treat it as basic operations? Multiplications. Yeah, because multiplications contribute the most to the total running time, right? Yeah, dominant multiplication part dominates the total running time. Yeah, so that's we treat it as basic operations, and so we have this concept. All right. Another constant we also need to consider, that is the execution time of a basic operation. Yeah. So because you need to run your program on your machine, and with respect to your own computer, you have this little C constant, C sub op, because on your machine, look at, when you run each basic operation, what is the execution time? Yeah, so you have a constant term. Yeah. All right. So then, now you can connect these two functions through this little constant. Yeah. So the formulas to connect those two functions, yeah. But here we need to take approximation approach. Yeah, because it's very hard to get the exact formula. So here we use the approximate version of the formula. Now, approximately equal. Now, T of n approximately equals C op times capital C of n. Yeah? All right. So this formula tells us these two functions are closely related. Capital T function, capital C function. Yeah. Closely related. Yeah. But the the constant part, little c constant part, for different computer, it's different. Yeah. Different machine. Yeah. This constant different. Yeah. But this relationship, for all the machines, yeah, we can use this relationship. Yeah. Then we can say, yeah, because T of n is approximately is the constant multiple of C of n. So we see their relationship is T of n is proportional to C of n. Proportional. Yeah. All right. So, and although this relationship is very simple, but we know these two functions, when we use them to measure the efficiency of the algorithm, C function is better than T function. Yeah. C function, because you just count the number of basic operations directly, yeah, that's stable, right? Yeah, that's stable. Yeah, yeah. But the T of n, not stable. Yeah. T of n for different machines, it's different. But C of n for all the machines, if the same algorithm, you get the same counting number. So, yeah. So we like to use C of n function to measure efficiency of the algorithm. All right. Yeah. Then, when we study the efficiencies of algorithms, yeah, because sometimes our formula expressions could be very complicated. Many terms, yeah, yeah, very complicated. So we want to simplify our expressions. So the approach we want to ignore unnecessary details. Okay? Now some details not that important, yeah, because we take the approximation approach, so we can ignore unnecessary details. Yeah. All right. Yeah. So some constant, yeah, for example, this little c constant, yeah, so this little c constant, when we take a special view, yeah, can we, is that very important, right? Yeah, so that little c constant, that can we ignore some minor terms, yeah, later, because when we have when our c function is a polynomial, there are many terms. Yeah. So if you take the leading term to represent the whole function, can you ignore the remaining minor terms? Yeah. So these two questions, yeah, we need to look at. All right. Now, let's take the ratio. Yeah, because when we consider the efficiency problem here, we want to see for each function, t function, c function, for each function, we want to see how fast this function increases. Yeah? So we know, so usually the function increases when the problem size n grows, right? Yeah, yeah. But how fast is the increasing rate? Yeah, yeah. We know in calculus there is a concept called the rate of change concept, right? Rate of change concept. That's the derivative. Derivative gives the rate of change concept. Yeah. The larger the derivative, the faster the increasing rate, right? Yeah. So that's the calculus way. But the derivative concept cannot be used here. So you will see, because the reason, the variable here, n can only take values, numbers from 1, 2, 3, 4, 5. So we call it discrete values. N can only take discrete values. So for functions, you can only take discrete values. Derivative is not defined. Derivative can only be defined when your function take the continuous value. Okay? Not discrete value, continuous value. Yeah. So here we cannot use the derivative concept. So here we use this ratio to represent rate of change. Fraction, ratio, numerator, we double the problem size. Okay? Double the problem size. Yeah. So the function value should be larger than over T of n. Yeah. And we want to see if this ratio large, very large, or not that large. Yeah. So for each function, we can use this ratio to tell us how fast this function increases, to replace that rate of change concept. All right. Here you can see, based on this approximation formula, when you do these two ratios, little c constant cancel out, right? Cancel out. So they have the same increasing rate. Yeah. So this formula tells us. Yeah. Although, yeah, these two functions have different meanings, but they have the same increasing rate. Yeah. Then we just use the stable version, right? C version. Yeah. So we do not need to use the unstable version, T version. Yeah. The stable version, it can give us the same increasing rate than the, execution time way. Yeah. Same increasing rate. Yeah. All right. Yeah. So now you can see from this formula, you can see this little coefficient can be ignored, right? Little c of coefficient. Yeah. Not that important. Yeah. So that can be ignored. Yeah. So it can simplify our discussion. We do not need to talk about constant anymore. Yeah, not important. Yeah. All right. Yeah, so here. Next. Yeah. Now, we just focus on this C function later. Yeah. Next, we need to talk about growth function concept. Yeah. All right. First, we look at the major term of an efficiency function. Major term, minor terms. All right. Yeah. The major term here, yeah, in part C, we use another concept called a dominant term. Yeah. So here, the same meaning. Yeah. All right. Let's recall the selection sort. So we have the efficiency function, right? Yeah. Yeah. So we count the number of comparisons. So this is our efficiency function. Okay? But this is the C function, right? Because we count the number of comparisons. Yeah. So this is the C function. This function has two terms. First, it's a polynomial with two terms. First term, second term. The first term is the major term, is the dominant term. Second term is the minor term. Yeah. All right. Yeah. Next, we need to see, yeah. We know the first term is larger than the second one. But the question, how much larger? How dominant it is? Yeah. You want to, yeah, so why you call it dominant term? How dominant it is. Yeah. So we need to understand, yeah, yeah, why you call it dominant. So let's do some simple calculation and see how much. So if we compare these two terms, we take the ratio of these two terms. We want to look at how large is the ratio of. All right, yeah. Here we take the limit when n goes to infinity. Take the limit, yeah. Because when n is very large, then we want to look at the limit of the ratio. How large is the limit? Yeah. Yeah. So why we consider n goes to infinity? Yeah. Yeah. Because when we study algorithms, we worry about the situation when the problem size is very large. So that's the difficult part. When n relatively small, right now we have, our computers are very powerful, right? Yeah. So we don't worry about solving problems with relatively small problem sizes. But even your computer very powerful, when you solve the problem with huge problem size, still very hard, right? So, yeah, so that's the part we want to consider, the difficult part. We want to consider large problem size. So when n goes to infinity, yeah, so the problem size extremely large. We want to look at the ratio. All right. Then after simplification, the limit of n, when n goes to infinity, we know it is infinity, right? Yeah. The ratio is infinity. When we compare two terms, the first term over the second term, and the ratio, the limit of the ratio goes to infinity, can we call the first term dominates the second term? Right? Yeah? Yeah. Yeah. So we feel very comfortable. Yeah. So that's why we call it dominant term. Another question. If we throw away the second term, do you feel comfortable? We ignore second term. We use the first term to approximate the whole function. Do you feel comfortable? Yeah. Because the missing part is very tiny, right? Yeah. When n is very large, the missing part, yeah, the missing part is so small. Okay? So we don't worry about that. We don't worry about that. Yeah. So that's why we can ignore all the minor terms. We only keep the major term, the dominant term, when we want to simplify our efficiency functions. That's the first round approximation. Yeah, this is the first round approximation. So we do approximation. Okay? Yeah. Yeah. And the result of the first round approximation, we simplify the representation. Yeah. We simplify it, but we do not throw away too much, right? Yeah, very little. Very little. Yeah. All right. So that's for the second round simplification. Yeah. So right now you have 1/2 constant times n squared. The second round simplification. Yeah. How important is this 1/2 constant? Yeah, we know, yeah, double, right? So if you throw away 1/2 constant, so the expression you get, double it, right? Double, it looks like still quite different, right? Yeah. But here, let us think in this way. Because this leading constant, yeah, we know there is some importance, right? But if you take the ratio C of 2n over C of n, that leading constant cancel out, right? Yeah, that leading constant, 1/2 is gone. So if you look at this ratio, you use this ratio to represent the increasing rate, that constant is not important. So that's one way to view it, okay? Yeah, because we want to look at how fast the efficiency function increases. Yeah. In what rate? Yeah. So from that point of view, yeah, it's not important. Leading constant is not important. Okay? So that's the first view of understanding. Second, all right, another different view of this question, yeah. Characterization. The second view is the characterization view. So what characterization? Yeah. In our first class, think about, in our first class, we characterize our data, right? We define different categories. So then we organize our data in different categories. Yeah, so that's the characterization of data. Yeah. And here, we will do another different type of characterization. We want to characterize our efficiency functions. Yeah. When we talk about efficiency functions for all the algorithms, large number of efficiency functions, if we do not organize those efficiency functions, very messy, right? Yeah, it's hard to do comparisons. Yeah. So now we want to define appropriate categories to organize large number of efficiency functions. Okay? Yeah. So that's another view of understanding. And when we define categories, yeah, now, category 1, 2, 3 different categories. Yeah. We want to use the simplest possible function, but this function can provide us information about the increasing rate. Yeah, so this function can still give us the same rate of increasing information, but it is simplified. Yeah, simpler, right? Simpler. So we use it to define different categories of the efficiency functions. Yeah. All right. So here, with this understanding, yeah, characterization understanding, so we drop the leading coefficient. We keep the most basic part. Yeah, n squared. Very simple. Yeah, but this function can give us the same increasing rate of the original term. But it's simpler. Yeah. And another understanding is these two functions belong to the same category. How about that? Yeah, they are different. We agree they are different. Yeah. They are different by a different leading constant. But we put them in the same category. Still okay, right? Same category. Yeah. So with that, you can see at the end, we extract this n squared term from the original efficiency function, and we call this term growth function. the concept, growth function concept. That's the growth function concept. Okay? Yeah? So we can use the growth function to define a category. Yeah? So to see which category this algorithm belongs to. Yeah? Which category? Okay? Yeah. So using the growth function. Okay? Here. Simple growth functions. Yeah. All right. Next topic, B.2. Now let's compare two growth functions. Yeah. So now for two different algorithms, we extract two growth functions. Now we want to do comparison. Which algorithm is faster? Which one is slower? Yeah, we just compare their corresponding growth functions. Yeah, so let's look at the question first. Compare two growth functions. Now we can use the example we did. We solved problem number 6, element uniqueness problem. Yeah, we solve it. Okay. Yeah, but we use two methods, method 1, method 2, right? But which one is better? At this point, we don't know. Method 1 better, method 2 better. So now we need to compare their two growth functions and see which one is better. Method 1, the worst case, yeah, C function, growth function, it's that. Yeah. Remember, we do the global comparisons. Global comparisons. So the total number of comparisons, this function. All right. Then, method 2, the C function, first, organizing data, we need to use n log n, right? We do sorting. Yeah. We need to do sorting. Yeah. Quick sort, for example. Yeah. The best sort we can find. Yeah. So n log n. After the sorting, then we only need to do adjacent comparisons, right? Yeah? Because our data is in ascending order. When we check if there are two elements with the same value, we only need to do adjacent comparison, right? Yeah, because ascending order. We only need to do adjacent comparisons. Think about if there are two elements with the same value. After the sorting, you can find two adjacent elements with the same value, right? Yeah. Yeah. So that's pretty obvious. Yeah. All right. So in that way, efficiency function is this one. All right. Next, we need to extract growth functions from these two efficient functions. The growth function of the first efficiency function, n squared. Growth function of the second one, the first term. Yeah. N log n, dominant term, right? Yeah. So n log n. Yeah. So the next question, we need to compare these two growth functions. Yeah. To tell us which algorithm is faster, which algorithm is slower, yeah, so we can make our decision. So we should choose the second one or the first one. So let's do comparison. Yeah. So we use the ratio of two growth functions to do comparison. And when we take the ratio, we take the limit when n goes to infinity. we calculate this limit. Yeah? So when n is very large, what is the limit of this ratio? Okay, yeah. All right, so let's do the calculation. First, we need to simplify the ratio. After cancellation, n over log n. Yeah. So here, this log, you may ask me, what is the base of this log function? Here, I didn't mention, but we can use some, appropriate base, a, but this a should be greater than 1. Yeah. We assume the base of log should be greater than 1 because in this case, log function is positive. If the base less than 1, greater than 0, the log function is negative, right? Yeah, so it does not make sense. So our counting function gives us negative values, so it does not make sense. So our counting function should always give us positive numbers. So we assume log base must be greater than 1. Okay, all right, so then we just do the calculation. How to calculate this ratio? Yeah. So here I want to still give you different views. Yeah. Can you see the limit is infinity? Yeah, the answer is infinity, but I want to ask you if you can see it. The ratio is infinity, n over log n. We know both functions go to infinity. So infinity over infinity. Yeah. Infinity over infinity, what's that? Infinity over infinity. Yeah. Indeterminate form. Because it can be anything, right? Infinity over infinity could be anything. So it's indeterminate. Yeah, so, all right. How to see it? So here I use 2 different methods to let you see it. The first method, we do variable substitution. We do some variable substitution because first, when we see the log function, most people are not quite familiar with the log function, right? Yeah. Log function, relatively complicated. Yeah. So, if we want to avoid log function, let us introduce a new variable. We do variable substitution. We use a new variable u to represent the whole log function. Yeah. Then the log function is gone. So we will not see log function anymore in our expressions. Yeah. After this variable substitution. Then, by the definition of log function, we have n equals a to the u, exponential. And we use the exponential function, a to the u, to represent. That's based on the definition of log function. All right. Then let's go back to our ratio. Yeah. The ratio after variable substitution, we use variable u. U still goes to infinity, yeah? Because when n goes to infinity, u also goes to infinity, right? So u goes to infinity, but the ratio becomes exponential function a to the u over u. Now, can you see the limit is infinity when you use this variable substitution? Because the numerator is an exponential function. And we know for an exponential function, we know an exponential function with base greater than 1. Yeah. So here, although we didn't mention base, yeah, because here the base greater than 1, right? Yeah. So an exponential function with base greater than 1 dominates any polynomial. Dominates means when you take the limit, goes to infinity, it's infinity. That's our dominant meaning here. Yeah. So, yeah. But this is, people always use this this fact in everyday life. Yeah. But we can prove it mathematically. Okay. Yeah. It can be proved mathematically. Yeah. Later we will prove it. Yeah. Yeah. Here we just borrow this, common fact that people use in everyday life. Yeah. All right. That's the first method. Second method. Yeah. Now we need to really do the calculation. Yeah. We need to find the answer in a rigorous way. Okay? Yeah. So here we need to use in calculus, Calc 2, actually this topic, L'Hopital's rule, to calculate that limit. Yeah. All right. So let me show you how to use L'Hopital's rule to calculate the limits. All right. Limit of the ratio of the two, based on the L'Hopital's rule. Yeah. The limit of ratio of two functions is closely related to the limit of two derivatives of those two functions. Closely related, actually equal, but under some condition. So that's why at this point, I didn't write equal because there is an important condition we need to check. Yeah. But if that condition is available, then we can say they are equal. Two ratios are equal. So what's that condition? The condition is the ratio must be an indeterminate form. Yeah, I mean infinity over infinity, indeterminate form, right? Yeah. So in calculus, there's this concept, indeterminate form. Yeah. There are several indeterminate forms in calculus. One is infinity over infinity. Okay? Another 0 over 0. So here it's a form just to give you the idea, the look of the ratio of two functions. Yeah. 0 over 0. 0 means the numerator function approaches to 0. Denominator function also approaches to 0. So 0 over 0. Yeah. Also indeterminate. Yeah. And there are many indeterminate forms. For example, infinity minus infinity. Indeterminate, right? Yeah. It could be anything. Yeah. Yeah. And let's say 1 to the infinity, also indeterminate. Right? Yeah. So there are many. Yeah. But for our class, we only use the first. Because our efficiency function always go to infinity. Yeah. So numerator function goes to infinity, denominator function also goes to infinity. So our indeterminate form always the first one. Yeah. All right. Now, let's apply the L'Hopital's rule. Yeah. All right. Yeah. So several. Yeah. All right. Here, let me show you how to calculate this limit by the L'Hopital's rule. First, we check if it's an indeterminate form. Yes, infinity over infinity. So no problem. If it is not an indeterminate form, then you cannot apply the L'Hopital's rule. Okay? All right. Now, we take the derivative of numerator denominator function. Denominator derivative, very simple, 1. Yeah, by the power rule, right? The power rule of derivative. Okay? So it's 1. Yeah. Yeah. numerator determinant, yeah. So we can, you can find it somewhere, right? Yeah. Sorry. Natural log of a, parenthesis, constant, times original exponential function, a to the u. Yeah. All right, yeah. So after simplification, yeah, you can see when u goes to infinity, this whole fraction goes to infinity. Yeah. Yeah. So that's the L'Hopital's rule. All right? Yeah. Yeah. The first example, we apply L'Hopital's rule. Yeah. All right. But here, because you take derivative, so there is one important question. I mentioned a few slides before, for a function to have a derivative, the function needs to use continuous variables. But here, actually our u is not quite continuous variable. Yeah. Our u equals log base a of n. Yeah. Still not quite continuous function. So still there is some hidden problem. There is some hidden problem here. Okay? All right. So, but now I use another version of the ratio. Let's calculate this limit. I want to show you how to get around that derivative problem. Derivative, yeah, because in this case, n function, log of n, the variable are discrete variables, right? Yeah. N variable takes the discrete values. 1, 2, 3. Not continuous variable. Yeah. Not continuous variable. 1.1, 1.3, yeah, continuous variable. Yeah. That means for these two functions, the derivative does not exist. The derivative is not defined. So we need to find a suitable way to get around this discrete variable problem. Yeah, so here, let me give you the technical treatment to make it work, yeah, to get around this technical difficulty. All right. Now we consider, because here we hit some roadblock here, right? Yeah, we hit some roadblock here. So we want to make some change on this ratio. So the change, we consider another ratio, similar ratio, x over log of x. Yeah. Here, x here, we use continuous variable. We do not use discrete variable. Our x can take all values greater than 1. Let's say greater than 1. Yeah. Yeah, because otherwise, if x less than 1, the denominator is negative. Right? Yeah, we don't want to consider the negative function. Yeah, we only want to consider positive function. So here we can assume x greater than 1. So we only have positive. Right. For this version, you can see the form are the same, right? But variable types are different. Discrete variable type, continuous variable type. For the continuous version, we can apply L'Hopital's rule. The derivative exists. So we can take derivatives. So let's do it. L'Hopital's rule. Yeah, because it's an infinity over infinity indeterminate form. So we can apply L'Hopital's rule. Derivative of x is 1. Derivative of log base A. Now, here we assume base A. Log base A of x. That's the reciprocal of natural log of A times x. Yeah, the formula. So you can find it somewhere, okay? From a calculus book or web search. Yeah, so you can find the formulas. Yeah, because how to memorize, right? Yeah, how to memorize all those formulas. Yeah. So you just find it. Yeah. All right, simplification. After simplification, natural log of A, parenthesis, it's a positive constant, right? Yeah, it's a positive. A greater than 1, so it's a positive constant. Positive constant times x, but x goes to infinity, it goes to infinity. The limit is infinity. Limit is infinity, then we need to make our conclusion. Yeah, because we modify our original ratio slightly, right? Yeah, we modify slightly. We change it from discrete variables to continuous variables. That's the main change we do here. Yeah. But for the discrete variable, our ratio is infinity. No problem. All right. The next question. Can we come back to say the original limit also infinity? Yeah. Now we want to get back to our original limit. Yeah. Yeah. To make the final conclusion. Okay? Yeah. We want to, based on that, we want to say this is also infinity. Yeah. But the question is, how can you do it? Why you can do it? We need to answer that question. Yeah. Let me explain. First, the answer is yes, you can do it. It's legal. No problem. Yeah. But I want to explain why it is legal. Okay? Yeah. Why it is legal. Yeah. All right. Yeah. So the reason you can do it in that way. Yeah. All right. Yeah. All right. From the definition of limit. Definition of the limit. When we define it, here I do not want to show you the definition of the limit. I just describe the main points. Yeah. When we say the limit is infinite here, when you look at the x goes to infinity, this part, okay, x goes to infinity. Did we say in which way x goes to infinity? In which way? Because there are millions of ways x can go to infinity, right? There are millions of ways x can go to infinity. Okay? Yeah. So for example, let me give you a few examples here. All right? One way, so x we take a sequence here, yeah? Because x goes to infinity, we take a sequence. The sequence goes to infinity. Okay? All right. 1.1, how about that? The first number in the sequence. 2.1, how about that? 3.1, how about that? 100.1, how about that? Right? Yeah. 1000.1, all the way to the infinity. How about that? This is one way. X, the sequence goes to infinity, right? Yeah. Yeah. All right. Another way, yeah. Root of 1, root of 2, how about that? Root of 3, root of 101, for example, and yeah. All the way to the infinity. is that this sequence also go to infinity, right? Yeah. So you have millions of different ways to make x approach to infinity. Yeah. All right. In the definition of the limit, anyway, if it goes to infinity, it's a valid way. Anyway is valid. If the sequence goes to infinity, then it's a valid sequence you can use. Yeah, that's the definition of limit. Okay? Now, yeah, so any sequence goes to infinity, it's a valid sequence we can use. How about we use the sequence 1, 2, 3, 4, and to infinity? That's the discrete values, right? If we take this particular special sequence to make x approach to infinity, we get that, right? Yeah. So based on the definition of the limit, when we jump from the continuous version, yeah, because we have the result, okay, back to make the conclusion on the discrete version of the limit, we can say it's also infinity. Yeah. Because we just take the special sequence, discrete value, consecutive positive integers as our x sequence to approach to infinity. Yeah. So, no problem. Yeah. Legal. Okay? All right. So we answer this question. After this, yeah, we do the comparison. Numerator n function corresponds to method 1, right? Denominator log of n function corresponds to method 2. Now can you tell me which method is better? Method 1, method 2, which one is better? For the element uniqueness problem, if you have the freedom to choose, which one you want to choose? Method 1 or method 2? Lauren, which one you want to choose?
Method 1, if it's a simple variable. Method 2, if it's a more complicated one.
Yeah. Method 1, we do not do sorting. We just do comparisons directly. Method 2, we do sorting first. We sort the array in ascending order. Then we do comparisons.
I find the
Yeah. Limits, that's the, calculation. So when we do comparison, we do the calculation. Yeah. Oh, you mean the method 1, method 2, limit of limit. Oh, okay. Yeah. Not the limit. Method 1, method 2 for the element uniqueness problem.
I was thinking the same thing.
Yeah, okay. Yeah. All right, you're confused. Right. So now go back to the problem, the solutions. Method 1 solution, method 2 solution. Yeah. The numerator corresponds to method 1 solution. Denominator corresponds to method 2 solution. Okay? Now, you have the result. The ratio goes to infinity. So, you make the final decision. Yeah? So, yeah. It's obvious, right? Yeah, method 2. Yeah. Method 2. Yeah. The growth function grows slower. Yeah. The method 2, the growth function grows slower, right? The slower, that means the algorithm is faster, right? Yeah, algorithm is faster. Yeah. Yeah. See? Yeah. So get the idea. Okay? Yeah, here. Yeah. Yeah. Yes. Which one is best? Yeah. That's how we go, right? Yeah. Why we do this, right? Yeah. The reason we want to really, because we want to, the question is, consider when the problem size is very large, which algorithm is better? Okay? Yeah? when the problem size is not that large, which one better, it may not be important. Yeah, because we only, so our concern only on the problem with large problem sizes. Yeah, so that's our main concern. Okay, all right, yeah. Yeah, so the conclusion, okay, yeah, all right. V.3, bubble sort. Yeah, yeah. Another interesting, our second sort. Yeah, so let's do part of it, yeah, of this. The same problem number 5, but we revisit. This time, we will view this problem differently, yeah, using a different angle to view, to understand the problem. All right, yeah. So let's look at this data. This is our data. Yeah. Now, we want to compare two elements in the array. Yeah. But this time, our understanding, yeah, so we need to find some properties, right? Yeah. We need to find some properties. Yeah. So this time, yeah, we want to consider the situation these two elements are out of order, not in order. Okay? Yeah, because our goal, making all the elements in ascending order, right? Yeah. If the elements, when you compare them, they are in the ascending order, then that's good. We like it. Okay? Yeah, because that is the same direction as our goal, right? Yeah, our goal, we want to get all elements in ascending order. Yeah. When we look at two elements, yeah, if they are in ascending order, then that's what we want, right? Yeah. But the problem is if they are not in ascending order, in opposite order, descending order. If you compare these two, and they are in descending order, then that gives us information something could be wrong, right? Yep. Undesirable. That situation is not desirable. Okay? So that tells us we should do something to fix it. We want to, yeah, because that is, not compatible with our goal, right? Yeah, our goal, make it ascending order, but it's in descending order, not compatible with our goal. Yeah. So we want to do something to fix it. Do some work to make it in ascending order. Yeah. That's our observation. That's our new understanding. Okay? Yeah. So, all right. So this observation for some critical property to solve the problem. Yeah. Let's look at this observation. If the array is not sorted, yeah, let's assume if the array is not sorted, okay, all right, there must be two adjacent elements that are out of order. Can you see this? There must be two adjacent, yeah. So you need to really think about it for a while to see this, if the statement is true or not. Okay, yeah, let me read it another time. If the array is not sorted, there must be two adjacent elements that are out of order. Yeah? Out of order means if you do comparison to adjacent elements, the first one is greater than the second one. That's out of order. The first one is greater than the second one. Yeah, yeah. So now you need to understand why, if the array is not sorted, then there must be two adjacent elements that are out of order. Okay? All right. Here, let me give you the how to see it, how to see this fact. Yeah, it's correct. This statement is correct. But why it is correct? Yeah. Here we use a method, a basic method you learn in also discrete math. Okay, there is a method, contrapositive method to prove a statement. Contrapositive here. Okay, all right. Contrapositive method. Okay, all right. So the method is, because in order to show this statement is true, you negate the condition. No, the condition. Yeah. Suppose the array is sorted. Okay. Yeah. Yeah. Think about. Yeah. Not sorted. Yeah. So actually, sorry. You negate the conclusion. Okay. All right. So, non-negate. Yeah. So here, this part is the hypothesis. This part is the conclusion. Okay. Conclusion. So contrapositive, you negate the conclusion. Then you derived negation version of the hypothesis. Okay, that's the contrapositive method. Yeah. All right. So you negate the conclusion first. All right. What's that? There must be two that are out of order. Now negate this conclusion statement. All other adjacent elements are in order, right? Yeah. There must be two other adjacent out of order. The negation of this sentence statement is all other adjacent elements are in order, in ascending order. That's a negation, right? Yeah. Negation means this is incorrect. This whole sentence is wrong. Incorrect. Yeah. Incorrect. That means all other adjacent elements are in ascending order. To make this one incorrect. Yeah. All right. So the negation of conclusion statement. Yeah. Think about. If all of the adjacent elements ascending order, you just draw the first of the adjacent ascending order, second of the adjacent ascending, all the way. You connect all of them, the whole array ascending order, right? Yeah, because every two of the adjacent, you take the first two ascending, take the next two also ascending. You keep doing. Every time you take two of the adjacent elements ascending, all the way to the end. Is the whole array in ascending order? Yes. If the whole array in ascending order, is it the negation of the hypothesis? Hypothesis tells us the array is not sorted. That means the array is in ascending order. It is sorted. That means you get a contradiction. If you get a contradiction, that means this one is correct. Okay? So when array is not sorted, the conclusion must be correct. That's the contrapositive method. Okay? That's the contrapositive method. Yeah. So we see it by contrapositive method. All right. Yeah. Next. Another state, so here I give you the reference. So I'm working on a file containing all the references. I haven't completed. I did the first 3 modules. There were 2 more modules. So I will complete it. All right. Then Yeah, so we will near the end. Yeah, because again, some students came in late. Yeah, because today is special. I need to leave a little earlier, so I need to talk to a professor about my PhD student. Yeah, so I need to. His office hour is right now, so I need to go to his office. All right, let me stop right here. Yeah, because next I need to talk about inversion concept. Yeah, so it takes quite some time about inversion concept. So let's stop right here.